So power. So we know that we've been talking about energy. We talk about different energies, okay? So power is the rate at which energy is transferred from one form to another. So the rate at which the gravitational potential energy changes into kinetic energy. So how quickly it does. And you can work out power using this equation. So P for power. And power is in units called watts, or just capital W, is the energy, which is in joules, divided by the time in seconds. So a bit of history, you don't need to know the bit of history, but just for information, the unit of power is named after James Watt, who is a Scottish scientific instrument maker who redesigned and improved the steam engine invented by Thomas Newcomen. Okay. So one problem he had was to sell his steam engine to industry. At the time, horses were used a great deal to operate machines, so Watt decided to compare his engine with a horse. So Watt decided to measure the time taken for a horse to do some work. Using a strong dray horse, he got it to lift 45 kilogram mass of a mine shaft, found that it could do this at a speed of 1.1 meters per second. In other words, he moved a distance of 1.105 meters in a time of 1 second. So every second he moved that much. The work done by the horse in 1 second was therefore, we know that work done is force times distance. So work done is mass times gravitational field strength times distance, because it's going up. Yeah, so it's basically your potential energy. So 45 times, it's estimating it to be 10 times by the distance that it travelled. So the work done was 497 joules. So to try and give as fair an estimate as he could for his engine, he then multiplied the horse's work output by 1.5, just to give it a fair advantage, basically. He then estimated that a horse could do about 746 joules of work in 1 second if it was really pushed. So a horse would have a power output of 746 watts. And he then used this unit of power, the horsepower, which you might already have heard about if you know about your sort of cars and your engines, to measure the output power of his steam engines. So the horsepower is no longer used as a standard unit of power, although power outputs of car engines are sometimes quoted in horsepower. A typical family car has a power output of about 150 to 200 horsepower, and it's now more common for this to be given in kilowatts. So 85 horsepower is 85 times by that value there, which was 1 horsepower, which is 63,410 watts. Okay, so you might have heard of horsepower being used before, and that's basically what it is. Okay, so we don't use horsepower anymore, but it was basically just something to compare this new steam engine, these trains that he just invented, to horses, and to say that, like, look, these are much better than horses because this could go this many times that a horse could go. Okay, as I said, you don't need to know the history behind it. It's just a bit of information for you. Right, we're going to skip the next page because we're going to come back to it in a second. I just want to go through a little bit more theory. So this is an extension exercise. That means it's not actually in National 5, but it actually fits in really well with this part of the course. So it's good to know, and it is actually really good to know sort of in an everyday situation. So you've probably heard the word efficiency. So how good something is at doing its job. Okay, so we're going to talk about how you work out something's efficiency. So levers, inclined planes, and pulleys are all examples of simple machines in physics. When machines transfer energy from one form to another, energy is degraded into other forms, so usually as heat due to friction. So we lose some of that energy because of friction. This means that not all the energy put in comes out as useful energy. So if you were talking about like maybe a crane, okay, you put in a certain amount of electrical energy or something like that into a crane, okay, not all that energy goes into lifting something. Some of it gets lost as heat and sound and things like that, and that's why it's not 100% efficient. If all the energy you put in came out as, you know, useful energy, so as the lifting energy, then it would be 100% efficient. But there's nothing that's 100% efficient. So the efficiency of a machine can be used using this calculation. So percentage efficiency is useful output energy divided by the input energy times 500. And as power is a measure of the energy transferred each second, then you can also say percentage efficiency is useful output power divided by input power times 500. Yeah, exactly. Yeah. So, for example, a winch powered by an electric motor is used to lift a 50-kilogram sack from a lorry to a platform 3.6 meters above. The electric motor is supplied with 16 kilojoules of energy. Calculate the efficiency of the winch. Right, so it's supplied with, so our input energy is 16 kilojoules, so 16,000 joules. We need to know the output energy as well, so what it actually does, the output, the useful output energy. So to find that, it's a winch, so its job is to lift something up. So its job is to give potential energy to whatever it's lifting. So the useful energy is the potential energy that the thing gains. So the output energy is mgh. So it's at 50 times by 9.8 times by 3.6, which comes to 1,764 joules. So you can already see that although it's been given 16,000 joules, its actual power that it's output, its useful output power, is just 1,764. That's its job, to lift it up. So there's been a lot of it lost as heat, sound, things like that. So to find out the percentage efficiency, so I just go percentage of F, just for ease, is your useful output energy divided by the input energy times by 100. So our output energy we worked out to be 1,764. Our input energy 16,000 times by 100, and that comes to, basically, if you round it, it comes to 11.0%. So not very efficient at all. So you will be doing some questions based on these in a second, but I'm going to talk you through the experiment that we're going to do first of all. So I'm going to be taking one group at a time. Well, one group at a time is going to be running up some stairs. So the rest of you can be doing questions while that's happening. Okay. Right, is anyone still writing? Right, so back to page 11. So you guys, sorry. The efficiency, I don't think so. I'll double check for you. The efficiency? Oh, the power. You need to know power, yeah. Right, okay. Listen. Daniel just asked, yeah, you do need to know power. You need to know how to calculate power in the test. Okay. Right, so this experiment is to measure your own power output. Okay, or one person from a desk power output. Or if you don't want, if nobody from your desk wants to do it, then you can nominate somebody else from another group to do it as well. Okay, so to find power, we know that power is energy over time. Okay, so what we're going to do, we're going to find the power output just running up this first flight of stairs just here, just next to my lab. Okay, so the power that you're going to be gaining is what type, the energy that you're going to be gaining is what type of energy as you go up the stairs. Up the stairs, you go to the top of the stairs, potential energy, yes. So you're going to be gaining a certain amount of potential energy, gravitational potential energy, and you're going to measure the time it takes for you to gain that energy. Okay, so that could be trotting up the stairs, it could be walking very slowly up the stairs, it could be running up the stairs. Okay, you just need to be careful when you're doing it. So our method, first thing that we need to do, and I've done this for you already, is measure the height of the stairs. So as I said, I've done that for you already, it's 2 meters. Then we need, because potential energy, we need m, g, and h. We've got a g, we know it's 9.8, that's the height. We also need to know the mass. So we need to measure the mass of the runner or the walker. And I've got some bathroom scales over there to use. As I said, if you don't want to measure your mass, you can make it up if you want. Right, so then what we do is we find the potential energy gained using mgh. Then, because power is energy over time, we need to time how long to get up the stairs. Then we just find the power by taking our energy, our potential energy, and dividing it by the time. So your results are going to be, write down your mass. We know g is 9.8. We know the height is 2 meters. And we need to measure the time. So your results will be EP equals mgh equals something. And then your power is that potential energy divided by time. And your conclusion will be basically the power output of somebody, whoever's doing it. You can all do it if you want, if you've got time, is something watts. You will, when you're going up and down the stairs, you'll need to wear your mask just because you're in the corridors. Sorry. So just be aware of that as well.